everyone, my name is Anmol Kaur. This is the first official video to my YouTube channel, The A-Level Chemist. And the reason I am doing this channel is because my main focus is to help students in STEM who struggle initially during the last 2-3 years of high school, and to just sort of give them not only teach them the content but also to give them some advice. So, what makes my channel different is I'm actually going to be using the syllabus as a constant reference to what I put out. And another touch I will be adding is at the end of every topic, I will post a separate video based on actual exam problems, which I will solve kind of like a worksheet. So, I will sample topical questions based on each and every different topic, and also just a little bit of personal touch in between the videos, like tips what worked for me when I was studying, and just some advice. So today we're just going to start. We're gonna look at the syllabus first of all. Just want to take you through it. Today's topic is basically gonna be the first AS chemistry topic. So before that, I just want to break down what AS and A level actually mean. Okay, so these are all of the papers that we have. We have paper 1, multiple choice. This is just showcasing. This is basically just the weightages. So if you want to know how much importance a paper holds in your marks, this is where you would go to. If you don't choose to do A level and you just want to do 1 year of chemistry, you just want to do AS Chem, then what you are going to do is just three papers, paper 1, 2, and 3. But if you're going to do all five, which is the full A level, then you will have to do all five papers. And technically it depends on you, and if you think you can handle A level pressures. I chose to do the full A level because it was required for my university and my program. We have the very first topic, which is atomic structure, also the first topic in IGCSE chemistry, but we're just going to go a bit deeper. Well, the first few objectives or the learning outcomes, as they say it. So, we need to be able to understand that atoms are mostly empty space surrounding a very small, dense nucleus that contains protons and neutrons. So, this is just, a basic model of the atom. And we have our dense nucleus here, neutrons, and then protons, and then these are our electrons, and then the empty space. So basically, this is just what makes up all of the mass, as you already know. Uh, and then this is a useful table. Sometimes it does come in the paper, but also it's just helpful to know that we know that a neutron is neutral, so it has charge of 0, proton is positive, and electron is negative. And then we have the mass. Since the nucleus is dense, it makes a lot of sense that it would have most of the mass there, which is why you see a relative mass of 1 for both proton and neutron. The electron is effectively 0, but if you want to be accurate, you can specify the fraction here. So these are some definitions that you should know because these are free marks. Once you know these definitions, it's really easy to just grab up 1 or 2 marks. And yeah, it's very simple to understand. The number of protons in the nucleus of an atom is the atomic number. The number of protons plus neutrons, which is essentially the entire mass of that atom, which is why mass number is here. And yeah, donated by denoted by A, and this is denoted by Z. Oh, this is something that is quite important to know. So basically, what we have here is an electric field. So you have positive charges on one side, negative charges on two sides. These are like two different plates, and the difference between these two charges sets up an electric field here. So when you shoot, let's say when you like shoot a particle across through this field, depending on how that particle is charged, whether it's a positive particle, a negative particle, as you know, negative particles are attracted to a positively charged plate. So that's where this electron goes to. You can see the protons being also attracted to the negative side as they are positively charged. The reason the arrow is longer and it seems like the proton takes more time to reach the negative side is because it's heavier. The mass of the proton the mass of the proton compared to the electron is 1. So essentially, the proton will be attracted to the negative plate slower. And then the neutron just moves across freely with no deflection. And yeah, this sometimes does come up in MCQs, so it's a very useful thing to know. This is just a few examples of how to write the how to write the atomic number, the mass number of an atom, an ion. So over here, this 2 is basically the number of protons. So this is the atomic number, the one at the bottom. Usually the lower number, the smaller number is the atomic number. So that kind of gives you an idea of what the mass number is. Because the mass number which was A is the sum of the neutrons plus the protons. So clearly the protons would just be the smaller number. So therefore we can assume that helium, which has a mass number of 4, would have 2 neutrons and 2 protons since it already has 2 protons. And then you can work that out for everything else. This plus and minus just basically tells us the plus and minus tells us whether the particle has an electron less or an electron more. So these are trends. Hold on, let's go back to our syllabus and tick. So the first objective is done, so is the second and third, and then we have the fourth one. Well, the fourth one, which says describe the distribution of mass and charge within an atom, it's basically asking you to describe that it has in a dense nucleus, so most of the mass is concentrated within the center, within the nucleus. That's um that's what it means by distribution of mass. And then you have the distribution of charge. The distribution of charge is basically talking about how the electrons are orbiting the atom, orbiting the nucleus, kind of like. And then you have the protons inside the nucleus, so like a positive center and then a negatively like charged kind of cloud orbiting that center. That's what this means. So we can easily tick that. Then describe the behavior of beams moving at the same velocity in an electric field. Same velocity is just same speed. So it just means that all of these three particles are traveling at the same speed. So that way we can easily compare how they move or how they behave. And then determine the number of protons, neutrons present in both atoms and ions. Yeah, so we've done that. State and explain the variations in atomic radius and ionic radius. The radius is just how big the atom is. So a large atomic radius means the atom is very large. Small atomic radius means the atom is very small. So here I compared lithium and oxygen to describe the trend across a period. In the periodic table, the period is basically, so if the periodic table looks sort of like this, sorry for my drawing, the period would basically be all of the elements in a row. So that's the period. And we're basically describing how bigger or smaller the atoms get as we move across this period. So atomic radii decreases due to an increase in proton number. The proton number increases. What we have is, as you can see, let's say this is the atomic number. So sodium has 11, magnesium has 12. So it increases across this period, 13, 14. So as atomic number increases, the atomic radii decreases. You may ask why. Well, this is because the number of electron shells remains the same. So in a period, let's say this is period number 3. If this is period number 3, each and every atom in this period and will have the same number of shells, that is 3. So in IGCSE, when you draw electronic configurations, you draw the number of shells. So if this is an atom, let's say A, and it has two shells, this is the nucleus, you just draw the first shell and the second shell, right? So in period 3, there would be 3 shells for each and every atom, despite how many protons they have. When we have the lithium atom versus the oxygen atom, since there are 3 protons in the lithium nucleus, these 3 protons will attract the 3 electrons in the 2 shells. But since the oxygen atom has 8 electrons, which is essentially more, these 8 electrons will have a more attractive hold over these 8 electrons. They will pull them towards the nucleus more, and so they will decrease the distance between the nucleus and the outermost shell. Hence, they will reduce the atomic radius. But for the lithium atom, since there's fewer protons, they will not be able to attract these 3 electrons as much. I think of it as, think of, because we already know how lightweight the electrons are, let's say. Their weight compared to the protons is essentially zero. So if you have more of these, let's say we have like a bunch of muscular guys, like these are just a bunch of muscular people pulling a bunch of lean people, like very thin people. Obviously, they will be able to pull them better. But if there were a greater number of these same muscular people, they would be able to pull those skinny people even better, no matter how many of those skinny people there were. You increase the force, therefore you're decreasing the distance, because they're being pulled, sorry, because they're being pulled even tighter. So you reduce this distance, if that kind of makes sense. That's essentially what this is. That's So that's for across a period for atomic radii. Ionic radii, it does decrease similarly, because for the first two groups in the periodic table that we have, like let's say this is group 1 and then this is group 2, from IGCSE chemistry, we know that they have positively charged atoms, which become ions, so cations. But then once you have, sorry, this is very thin, but it comprises of, group 3, 4, 5, 6, 7, and 8. But group 3 and 4, they are basically group 3 is definitely positively charged, but group 4 can either be positive or negative. So you get to that metalloid area where you have semi metallic properties, sort of, where you have your silicon, your other elements like carbon. So those ones are a bit of a gray area. But then you have your anions, your fluorines, your oxygens, and all of that, nitrogen. So for those become anions, and then you have your cations. So ionic radii will initially decrease a, sorry, along the metals. The metals meaning, like, let's say we have sodium, we have magnesium. So like, I'm taking period 3 as my example. So you have sodium, which will become Na plus. You have magnesium, Mg2 plus, aluminium 3 plus, silicon most likely will be 4 plus. But then you have phosphorus, which becomes 3 minus. Then you have sulfur 2 minus, chlorine minus. Argon is remaining neutral. It's a noble gas. So the reason it would initially decrease is the same for the atomic radii. So sodium would lose one electron, becomes Na plus. So let's remove the outer shell, and then you have more number of protons pulling less number of electrons. So they're able to reduce that distance between the new outer shell, and the nucleus. That reduces your ionic radii, and that pattern is followed by all the metals. The reason that it decreases is because, as you go along, the proton number increases. So you have a more number of protons pulling in those outer electrons. But then it increases along the non-metals due to the loss and gain of electrons, which affects the overall charge. So for example, once you reach the phosphorus becomes 3 minus, so it gains 3 electrons, so there's less number of protons available to pull more number of electrons. So that would just increase that distance, because those electrons will now be able to sort of reduce the impact that those protons have on them. So yeah, that's basically about atomic and ionic radii across a period. When we talk about them down a group, so let's say along group 1, atomic radii increases because of an increased number of because an increased number of electron shells outweigh the increase in proton number. What does this mean? So down a shell, if I'm taking group 1, sorry, down a group, if I'm taking group 1, we have lithium, sodium, potassium, rubidium, cesium, and francium. Lithium would have just 2 electron shells. Sodium has 3, potassium has 4, rubidium 5, and so on. So as the number of shells increases, we automatically know that the distance between that outer shell and the nucleus is going to increase, because if you have just the nucleus and then the outer shell is 1, then later on it becomes 2, and then 3. This distance is slowly increasing, and then your radius is also increasing. So that's what it means, and that's very simple. That's just what it is. Even though the proton number is increasing, it cannot increase to that extent that it will sort of pull all of those electrons very dramatically inside, because the shell number is increasing. that overpowers all of the um, protons. And then ionic radii also increases for similar reasons because they have a similar charge. So plus 1. It doesn't matter because all of them as ions will be just losing one electron. So essentially, lithium will reduce from two shells to one shell because its only electron in that last shell is gone. But then that's the same case for all of them. So it again becomes the same reason for the atomic radius. So that's very easy to understand. Whether for cations or anions, this is the exact same trend that both of the radius follows down a group. So we are done for 1.1. Now we're gonna just move on to isotopes. Isotopes in IGCSE, same thing. There is no difference at all. So I'm not gonna go that much deep into it. Just a quick overview. You're supposed to know the definition of what an isotope is, which is the same as the IGCSE definition. And this is just using our common example of carbon 12. So we have carbon 12, which is what we commonly know. It has two isotopes, carbon 13, carbon 14. And yeah, this is just what being an isotope is. So the chemical properties will definitely be the same because it does have the same number of protons. Each of the carbon isotopes have 6 protons, which means that their chemical properties are unchanged. The mass number is different because they have different number of neutrons. So the mass number being different just means that different physical properties, maybe melting point, boiling point, density, and so on. That's essentially all there is to isotopes. There will be some calculation questions for isotopes, but we'll look at those in stoichiometry, which is in the second topic, not in this one. For this topic, all you need to know is the definition, and you just need to identify the different isotopes. So that's basically it for isotopes. Define them, understand the notation, state and explain why they have different physical properties, which I explained. Explain why they have the same chemical properties. Yeah. So it's a very simple topic, isotopes. So the third part, electrons, energy, atomic orbitals. This is where we go beyond IGCSE level. So this you've heard of electronic configurations in IGs, right? IGs, it was mostly if you have an electron, let's say it has 10, sorry, if you have an atom which has 10 electrons, your electronic configuration would be 2, 8, and that's it, right? But we go a bit further in A levels. So when you're starting, we're going to start to learn what this means. So this is an example of a very simple electronic configuration. So I've highlighted the different parts of it. Essentially, this whole thing is an electronic configuration. And what it means is you have two electrons in the very first shell and orbital of an atom. So, explaining this, the one is the principal quantum number, which is basically the shell number. So, like lithium has two shells, the first shell would have principal quantum number of 1, and the second shell would have quantum number of 2. That's what this means. Then you have the number of electrons. The number of electrons just, yeah, self-explanatory. It means if you have two electrons in one shell, then you write 2 for your number of electrons. It's kind of like a subscript, so it looks like squared, but it's not squared. Then you have the subshell. So within a shell, you can have different levels. So those are subshells. Those subshells have like orbitals. So if I'm talking about even a bookshelf, let's say we have a bookshelf in our cupboard or anywhere, they have different levels where you keep all your books. So let's say you keep all your you know all your novels here, sci-fi, um mystery, everything, fantasy. If you have different levels of organization, that's basically what a subshell is. And then within these, you may have different authors. So like let's say for novels, you may have, oh sorry, for novels you may have different authors. So that separates your book section. So you have author 1, author 2, author 3, like that. Those are what the orbitals are. And each of these orbitals within our subshells, they hold 2 electrons. So in our case, each author here has 2 books. That's essentially what this is. That's the organization system for shells within an atom. So here's just an explanation of the subshells. These are the different letters. So basically, the different um, names of all of those subshells. So, like you see how we had mystery, fantasy, novels. This is basically the same thing. So, S subshell, which is the smallest, so it can hold 2 electrons, which means it has one orbital only, because every orbital has 2 electrons. So this has one orbital, and then we have our p, the second largest, sorry, the second smallest, can hold up to 6 electrons. So that means it has 3 orbitals. And then and then we have d, 10 electrons, so 5 orbitals. F, which can hold up to 18 electrons, so that means 9 orbitals. In A levels, we usually don't deal with the f orbital, so you don't really have to worry about that. It's more of like a gray area. Not important, but it's good to know because it's mentioned in textbooks, so it's good to have a fair idea of what it means. But it's not mentioned in any question. You don't have to know how to write the configuration using an f kind of subscript or anything. These three are the main subshells that you have to know. So this is talking about the energy levels. So 1s is the lowest energy level. It's the first electron shell. um, I'm just gonna draw an atom beside here to show you. So we have our atom A. Let's say this is the nucleus. So first shell, this is your 1s shell. Your second shell, 2s. Within this 2s, you have these 2 subshells. Your 2p subshells and your 2. Oh, I'm sorry. This is just the second shell, not the 2s shell. 2s is a subshell. That's my mistake. So within the second shell, you have the 2s, 2p subshells. And then as we go on, we have the third and the fourth shells. And this is just showing us how the energy levels keep on increasing as you go higher and higher in shell number. So as expected, 1 has the lowest, then 2 is higher, 2s is less, 2p is more, then we have 3s, 3p, and over here a very interesting thing to note, 4s is lower in energy than the 3d subshell. This is a very important thing in electron configuration. Basically, how we assign electrons is, let's say if you had 3 electrons in your atom. Now the one s holds 2 electrons, right? Because the s orbital has 2 electrons only. So you have 3 electrons. We're gonna put two here. Sorry, we're gonna put 2 electrons here, and then we're gonna put 1 electron here in the 2s, in the next highest energy level. So that's how we sort of assign the electrons to each shell. And this is important because for this, what we do is we will, if we have enough electrons to keep going, and we have to put one in the 4s, sorry, we have electrons in the third shell, and we're still arranging them, we then start in the 4s before we get to the 3d. So if your 3p is full and you have more electrons, you put them in 4s before you do 3d. That's how it goes. But then once you're removing, you remove from 4 before you remove from 3, because you remove from the fourth shell before you remove from the third shell to get your ions. And it may seem very sketchy, but with practice you will get used to it. The main idea is just to keep practicing, especially when you're new to this topic. Practicing electronic configurations, writing them makes it so much easier. So we're gonna start with neon as our first example. It has 10 electrons, so we're just gonna start. So you write the 1s2 first, because 1s, first of all, you have to write the first shell, that is 1. Then you write the first subshell. 1, the first shell only has s. It cannot have p. There is no such thing as a 1p orbital, sorry, a 1p subshell. So we have 1s, and then it can fit 2 electrons, so we have 2. Now we're left with 8. So then you go to the second shell, 2s2, because s can fit 2. Now you're left with 6 electrons. The p orbital can fit 6, sorry, the 2p subshell can fit 6 electrons because it has 3 orbitals. So we're done with our electronic configuration. Now for very very large atomic numbers, so calcium is double that of neon, it's 20. So this is the long way, which is the traditional way of writing it, and I used to write like this for a very long time, in fact my whole years, because I didn't really like the shorthand way. But a lot of people will like the shorthand way, so I have to teach that as well. We have we have calcium, so 20, right? So obviously we can repeat what we did for neon up until 10. And so now the second shell can only have 2 subshells. Third shell can have 3 subshells. So the 3s, 3p, 3d, right? But as you know, the 3d is above the 4s in terms of energy. So we have 10 more electrons to assign after we're done with this. So 2 of that goes in the 3s2, 6 go in the 3p6, and then you're left with 2 more. And instead of putting those in the 3d, we put those in the 4s2, right? That's how you would complete your electronic configuration in a long manner. But some people would like to just put a neon core. So these are the noble gas cores, with core as in core. It's so this is a neon core. We have argon cores, krypton cores for even bigger atomic numbers. So since calcium is atomic number 20, you can simply use neon. So you have to define the noble gas core first. You can't just write the neon in the bracket and expect it to be understood, even though it should be. What you need to do first is write out the neon's electronic configuration, like as above, and then you can use it. So if there's a question which is like calcium, magnesium, let's say titanium, and all of those atoms, and you have to write all of their configurations, you can say defining this as that, and then you can later on write all of those configurations in the way that I wrote this calcium one. But that means you have to know what it is. So this is just for ions. As you know, earlier on in IGs, even when an ion was defined, when we had to write the electronic configuration of an ion, you would often write it as one electron less or one electron more. So it's the same thing. For the sodium ion, sodium atom has 11 electrons, so sodium ion has 10. So you just write it as the neon core. And then the chlorine one has 18 electrons, so you just write that. So it's simple, you just need practice, and you can practice by writing out the electronic configurations um, for all of the atoms in the third period or fourth period, in fact. Now, what we have is another way of writing electronic configuration, which is box notation. This makes my bookshelf example come to life, sort of. Each box is an orbital, so has two electrons, which is a very, this is the best way I like to write my electronic configurations, because it helps you visualize where all of your electrons individually are going. So you have your 1s uh, orbital, which fits two electrons. So as you can see, these two electrons have two opposing arrows. The reason is the electrons are both negatively charged, and so they repel each other. So what we have is a spin pair repulsion. So these two electrons confined in one space will always repel each other. So you tend to write them in different directions, which means they move, they spin. The electrons are basically like tiny, tiny magnets. So they have a sort of spin. So they will spin in different directions to minimize that repulsion so that they don't go away from each other and they remain in this space. That's why we write them with opposite directions, kind of like half arrows. So this is just how you draw them. The 2p, because the p subshell has three orbitals, so you just draw a big space and divide it into three sections, like the shell. So that's how you do box notation. And yeah, the two electrons repel due to like charges. So you often fill one at a time. So it means that because the electrons like to repel each other, if you have, let's say, something like this is just an example, and you have, let's say, 5 electrons, you first have to fill one by one. So 1, 2, 3, 4, and then there's no more, so you fill here 5. First you need to fill it one by one, and then you can start filling it, you can start doubling the electrons in each shell. You can't just start by putting 2 electrons in one orbital, because they tend to repel each other, so it's most suitable to do it one by one first. So like for example, the nitrogen atom here, nitrogen has an nitrogen has an atomic number of 7. So you have one, so you first of all fill it one, my bad, you fill it 1, 2, 3, 4, 5, then 6 and 7, and that's it makes the configuration way more stable, and it makes the atom stable as well. And just a side note, which will come in useful, half filled and fully filled shells are more stable than others, especially for D subshells. And this is mostly prominent or seen in transition elements. So these two exceptions you have to know, because these are very crucial, and these are the mostly common asked electron configurations, so these you have to know. They are chromium and copper, so they don't follow the normal electronic configuration. The 4s electron sorry the 4s shell, it fills first, usually because it is low in energy compared to 3D. That's what we would expect to happen. However, since half-filled 3D shell is more stable, an electron fills the last orbital there. So the 3D, you would expect the 4s to be 2 before we even start filling the 3D. But since 3D5 is more stable than 3D4, we have to half fill this before we fill this. So a 3D4 would sort of be like this. So it has 5 orbitals, and then a 3D4 would be like this. There's an empty orbital, and then you have your 4s2, which is like that. But we rather would prefer to remove this electron and sort of move it here for just to make it more stable. So that's the exception of chromium. Copper follows a similar pattern, except that for copper the 3D is fully filled. So over here the 3D is fully filled and the 4s is half filled. And it makes a lot of sense. It makes it way more stable. And once you write it out, you will eventually see why. Also, in A level chemistry, when you get to transition metals, it makes a lot more sense on why this is more suitable. So, yeah. However, when we're forming a copper or chromium ion, the electrons will leave the 4s first because it's the largest number. Forming ions, the electrons, especially positively charged ions, the electrons will always leave the largest principal quantum number shell first. That's always been the case. Okay, so another thing you need to know, the shapes of the orbitals. The s orbital is basically a sphere. So I have my y and my x axis, and then it's just a sphere. That's all you need to know. Very simple. P orbital is a dumbbell. So that's the shape of the p orbital. Since there are 3 p orbitals for each like subshell, what this basically is that this is the xy. There's a y p orbital, an x p orbital, and then there's a different one that goes like this way. Then we have this one as well. So that's like 3. It's a very complex shape to look at, but they won't ask you for that. They'll mostly just ask you to draw the shape of one p orbital, and you're good. Just draw the dumbbell, and that's fine. So we're done with all of these. Oh, and describe a free radical as a species with one or more unpaired electrons. That's just the definition. Nothing much for free radicals. One or more unpaired electrons. It's basically like whether or not it's like this. This one has an unpaired electron, nitrogen here. So the electrons aren't paired with each other. That's basically what a free radical species means. So that's that. We're done with electrons, energy levels, and everything. And we're moving on to the last part of this topic, ionization energy. So, ionization energy. First of all, the definitions. You need to know the definition of the first ionization energy, and then that what this means. Ionization energy, what it means to ionize an atom is basically remove an electron off of that atom to make it into an ion. And so the first ionization energy is the energy needed to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of gaseous plus 1 ions. Breaking all of this down, 1 mole of electrons, the 1 mole repeating itself is because of standard conditions. When we talk about standard laboratory conditions, we think of room temperature conditions, 1 atmosphere, 25 degrees Celsius, and all of that. So, 1 mole is basically standard. It's like you always have to use that. So, we're removing electrons from gaseous atoms to form gaseous ions, and it's measured in kilojoules per mole. Since it's energy, all energy in chemistry is measured in kilojoules per mole, and even the per mole, so how many kilojoules is being released every mole of atoms, which is why the 1 mole has to be present in the definition itself. So this is the equation for the first ionization energy. One thing to note is state symbols always have to be present. You cannot ignore that. It's like 1 mark when they tell you to write the equation. So from the definition, you're removing 1 mole of electrons from 1 mole of gaseous atoms. So we start with our gaseous atom, and then you get gaseous ions and a gaseous mole of electrons. But you don't use gas for electrons as a state symbol. It just doesn't work that way. Now, second ionization energy is the energy needed to remove 1 mole of electrons from 1 mole of gaseous 1 plus ions to form 1 mole of gaseous 2 plus ions. And if that makes sense, because it's second, we're removing the mole of electrons a second time. So we're removing them from the product of the first ionization energy. And so you just use your state symbols again. And we just repeat that for third, fourth, and successive ionization energies. So that's essentially what it means to define the term ionization energy and then constructing equations. So now we're going to identify certain trends in ionization energies. So before we do that, the trends use certain words and terms, and I just wanted to explain those terms and words before we use them. So we already know the trend in atomic radius. We explained that earlier. So the larger the atomic radius, the lower the ionization energy. This is because valence electrons face less attraction as atomic radius increases. So it does not require much energy to knock them out. So what does this mean? When your atomic radius is extremely large, what you have is the distance, the so the nucleus is not able to attract those electrons um, to itself. What this means is when you're trying to remove those electrons, you're not going to face much problems removing them, because the let's say the person that's supposed to be pulling them is not able to do their job well. So what you have is a result of a weakened force. So you're able to remove those electrons very quickly. So you don't need that much energy. It's like if someone is sitting here and they're pulling, let's say, an apple towards themselves or something, let's say by even sheer willpower or something, and you are here. If the person was closer to the apple, then it would be more difficult for you to pull it. It's like tug of war, right? This point within, let's say, a rope is much closer to you, so you're much in a much more better position to pull it towards yourself than that other individual is. That's essentially what the atomic radius and ionization energy relationship is. So that's how it affects ionization energy. Larger the atomic radius, the lower the energy, because the lower the effort to remove the electron. And you just have to think of it as, how much work do I need to put in to remove that electron? Because if you're putting in less work, that means you need less energy. If you're putting in more work, that means you need more energy. So that's for atomic radius. Then we have nuclear charge. As nuclear charge increases, ionization energy increases, considering that atomic radius does not increase. That's a very important note. So when nuclear charge increases, ionization energy increases. Pretty self-explanatory, but just to explain, if let's say the same example as the tug of war thingy, so if there's like two people now, instead of one person, there's two people who are pulling that apple towards themselves, and then there's just like one of you, you would face much more difficulty in pulling it back. So the larger um, the larger the number of protons, the more energy you have to put in to remove the electron from the valence shell. That's what nuclear charge means. And then we have shielding effect. When inner shells face the attraction from the nucleus and reduce that nuclear charge effect for the outer shells, making it easier to remove an electron and successfully decreasing ionization energy. What does all of that mean? Basically, shielding effect means that you have, let's say, a nucleus here. Nucleus is pulling these electrons towards itself, right? These two electrons in the first shell. So now the nucleus is not able, well, it's able to pull this last one as well. Not as effective as it can pull these first two, but it can still pull that last one. Now we have more shells. You have like a third shell. So the force this nucleus uses to pull these two is much greater than what it uses to pull the 8 electrons in the second shell. And then there's essentially very little sort of pulling force for this last electron. So nuclear attraction does not reach the valence shell, I would add, as effectively as the inner shell face the nuclear charge. So it's like the inner shells are facing most of the power and the force by the nucleus. So the outer shell does not face it as much. So you would need more effort to remove this electron than you would to remove this electron. So essentially, this has a larger shielding effect. The outer electron is shielded by the inner ones. That's what shielding effect means. So this atom would have a lower ionization energy compared to this atom. That's what shielding effect is. So now we have spin pair repulsion, which is when a fully my bad when a fully occupied atomic orbital has two electrons, those electrons repel each other. We already observed that. So it becomes easier to remove one of those electrons, which is very true. When you have these two atoms, all of everything till the 2s to sub orbital is the same. Now we have the 2p3 shells. uh, this is also the 2p3. My bad, that's the 2p3. So what we have is three different orbitals, but oxygen has one extra electron. So that electron would be put in here, and this orbital now has two electrons that repel each other. So if they repel each other, it just makes it so much more that they want one of them to be gone. So it makes it easier to remove it. So the two electrons face spin pair repulsion. So nitrogen has a higher ionization energy than oxygen. Or in simple words, it makes more sense to remove one of these electrons than to remove one of these electrons, since let's say even if these two were people and you like crowd them in one small space, you would want one of them to be gone to make room. So it takes less effort to sort of, I don't want to say convince, but convince the electrons, if that makes sense. And then that just makes the effort less, so ionization energy is less. So that's for spin pair repulsion. So these are all of the terms that you have to be able to use to successfully not just explain your case, but you can also get free marks just by using these words in the correct context when an ionization energy question comes in. So the last thing we're going to talk about is the trends in ionization energies. But first let me finish ticking. So okay, what we have, I have to actually tick these ones, this and that, and we're gonna do 3, 4, 7, and 8 or now. So trends in ionization, and now this will become much more easier to explain because I've explained those terms we need first. So across a period, the number of electrons increases in the outer shell while the number of shells remain the same. And you know what this means? It means atomic radius decreases. So this causes a decrease in atomic radii, which increases ionization energy. Shielding effect is constant. You have to always mention what is constant. So shielding effect is constant, which means it doesn't change because the number of shells are the same. And shielding effect only comes into place when you have different number of shells. So it doesn't work across a period. So what this means is that the nuclear attraction increases, and so the nuclear charge increases, atomic radii decreases. You can use those terms to help explain your case. So we have down the group the number of electron shells increase, so the distance between the nucleus and outer shell increases. And this also means that shielding effect increases, so it becomes easier to remove an electron from the outer shell. Hence ionization energy reduces down a group. So we also have to mention the increased nuclear attraction is constant, because it doesn't matter how much it increases, it remains constant because of the shielding effect. So that's the trend in ionization energies for across a period and down a group. And the last thing we need to know, successive ionization energies. So when gaseous atoms keep losing electrons one after the other, that it causes successive ionization energies, which means just repeatedly losing one electron. So this increases as more electrons are removed, which means it becomes more and more difficult to remove those electrons since this becomes overall positively charged. So the nuclear charge increases and it makes it more difficult to continuously remove those electrons. So um, successive ionization energies keep on increasing. So I just have this simple question here. We're going to use this to determine what group slash period this element is in. So we have an element A and we have its first seven ionization energies. So we have the first, the second, the third, fourth, fifth, sixth, and seventh. Now you will notice there is not a very significant jump between the first ionization energy, the second one, the third one, or the fourth and fifth. They are very similar. There is not much. You have to take into consideration a very large jump is the one that is between the fifth and the sixth. This is a extremely large difference compared to any difference you have between the first to the fifth. That's a much larger difference. So what it means is these five electrons were present in the same shell. The valence shell of our element A had five electrons. That's what this means. Valence electrons were five. And then you have the sixth and the seventh. And then it probably goes on. So what this means is valence electrons being five indicates that this element A is in group 5. We don't know what element it is, but all we can tell from this information is that it is in group 5. Sometimes you will often find yourself seeing questions like these, but for different things. So it could not be groups, it could be periods as well. They could give you much more information to help determine what is going on with this element. So let's finish our checklist. We've identified all of this. And with that, we're done with our first topic of A level chemistry. I will be putting timestamps and I will see you guys in the next video. Thank you so much. Bye.